We have here a diagram that we saw in a previous video. We have a surface z is a function of x and y, and in the xy plane we have a line parallel to the x-axis and a line parallel to the y-axis, above which we have curves on the surface that correspond to what would happen if vertical planes through the lines in the xy plane were to intersect the surface. And then along those curves, there's our tangent lines, right? The slope of the blue tangent line, that's the one above the line that's parallel to the x-axis. That's the tangent line where we're holding y constant. And so the slope of that tangent line is the derivative in the I direction. And here when I say the I direction, I'm talking about the unit vector I with components 0, 0, 0. I'm sorry, 1, 0, 0. Likewise, the green tangent line, I couldn't figure out where to write it here. The green tangent line is the derivative in the j direction. That's the one above the line in the xy plane parallel to the y-axis, and so holding x constant. What the directional derivative is a way to find the derivative or the slope in any direction that you like. Let's formalize that. The directional derivative allows us to find the derivative of f, a function of x and y, in the direction of any unit vector u given by AB, or if we have an angle, cosine of theta, sine of theta. In R2, where theta is the angle in the xy plane between the vector u and the positive x-axis. And now we're going to look at a different diagram from the textbook. But first, I want to point out that it's the direction of any unit vector. And one common mistake I see is that when we do computations, folks don't always find a unit vector before they get started. It is important that we are working with a unit vector. So here's our diagram. We have this surface S, which is in the first octant. And in the xy plane, we have a vector here, u, and it's just in some random direction. We have a vertical plane that is that passes through, or that contains u, and cuts the surface and gives us a curve. And at the tail of u is a point, above the tail of u is a point P on the surface, and that at that point is a tangent line, so it's given by T here. The point of tangency on the surface is P, which has got coordinates x naught, y naught, z naught. And then below that, in the xy plane, the tail of u, is the point P prime, which is x naught, y naught, 0. Now, away from P, some way along the curve of intersection between the plane and the surface, is a point Q, and Q, x, y, z is intended to be a random point on the curve, which is also on the surface. The curve here is given by C. The projection of Q onto the xy plane is Q prime, which has coordinates x, y, 0. And the points P prime and Q prime in the xy plane are a distance h units apart along the vector along the vector u, the unit vector. Now u has components a, b, and if we want to visualize these components here, we have in the x direction from the tail of u we would go A, and in the y direction we would go B, and that would give us the head of u. And I only gave you that to explain what's going on with HB and HA. It's intended that HA and HB are giving us components of a scalar multiple of u that has length h, because u was a unit vector. All right, so those are the pieces in this picture. The vector from P prime to Q prime is parallel to the unit vector u and is given by HA, HB, those are its components, and we can express it as H times AB, the vector, which is another way to say it's H times the vector u. You can confirm that X and Y for Q prime, which has the coordinates X, Y, 0, are X equals X naught plus HA, Y equals Y naught plus HB. One last thing before we write down a definition. The slope of the tangent line to the surface at the point P is the limit as h approaches 0 of delta z divided by h. So as the horizontal distance goes to 0, we get a derivative for z, right? And that can also be expressed as the limit as h approaches 0 of z minus z naught divided by h. All of that is to set up the following definition. The directional derivative in the direction of u, so it's a little subscript vector, of f at the point x naught, y naught is equal to the limit as h approaches 0 of f of x naught plus ha, comma, y naught plus hb minus f of x naught, y naught, all divided by h. Remember that u is a unit vector, and it's really giving us a direction that we're going to care about. The limit is called the directional derivative in the direction of u. It gives the rate of change of z, which is really the slope of a tangent line at P in the direction of u. Now, this definition is not how we're going to compute it. In order to get there, we're going to have to go through a little bit of a process here. Consider a function g of h that is given by f of x naught plus ah, y naught plus bh. Right? So those components x and y that we saw before that gave q. Then g prime of 0 is equal to the limit as h approaches 0 of g of h minus g of 0 divided by h. That's by the definition of a derivative in single variable calculus. And that will equal the limit as h approaches 0 of f of x naught plus ah, y naught plus bh minus f of x naught, y naught, all divided by h, which is the definition of the directional derivative of f in the direction of u at x naught, y naught. And you say, well, that's just what we came up with. I know, but what we're saying is that's one way to express g prime of 0. Looking through another lens, we can say that g of h is equal to f of xy, where x equals x naught plus ha, y equals y naught plus hb, and now what we have is a function f of xy where x depends on h and y depends on h. So g prime of h by the chain rule is equal to the partial of f with respect to x times dx dh plus the partial of f with respect to y times dy dh. And that can be written as fx at xy a, right, that partial derivative, f plus fy at xy b. And that's another way to write, or that's a way to write g prime of h. But if h is equal to 0, then x becomes x naught and y becomes y naught, because if h is 0, the ha and hb zero out. So the directional derivative in the direction of u of x at x naught, y naught, which is, we already said g prime of 0, given by the partial of f with respect to x at x naught, y naught, a, plus the partial of f with respect to y at x naught, y naught, b, where the first equality is by the definition of a derivative, and the second inequality we obtained by the chain rule. This gives us a way to compute the directional derivative. In general, the directional derivative in the direction of u of f of xy is equal to fx at xy times a plus fy at xy times b, where u is the vector ab and the magnitude of u is equal to 1, right? So it's a unit vector. I'm going to put that equation in a box. We're just about done with this portion here. A couple of quick things. If u, the unit vector, is the cosine of theta, sine of theta, then the directional derivative in the direction of u at xy is equal to fx at xy times the cosine of theta plus fy at xy times the sine of theta. If we're looking at f as a function of x, y, and z, then the directional derivative in the direction of u of f of x, y, z is, you probably already know, fx at x, y, z, a plus fy at x, y, z, b plus fz at x, y, z, c, where u is the vector abc and the magnitude of u is, again, 1.